today are the real hybrid machining processes, because there are more than 2 or more physical principles are taking place at the same time. That means simultaneously. Okay, so that means you can see that if you really want to model those process, or there are a lot of things you need to understand because of simultaneous interactions. On the other hand, whatever we covered in the compound machining processes, if you understand individual processes, and then you would be able to understand most of the compound processes. So that's good. So I try to kind of arrange in a way so that you now have understanding of more than 10, 15 different manufacturing processes, right? So now what are each processes, what physical principle is taking place, what is the main mechanism of material. Now you should be able to kind of combine them, and whether you can actually combine them for concurrent machining processes. So for today's plan, so first I'm going to cover the concurrent or combined or mixed or simultaneous hybrid machining processes, and then there are several compound processes I could not cover. I have prepared those, so I'm going to cover those after the tea break. So until tea break, I hope I would be able to finish those. And then after tea break, I'm going to use maybe half an hour to 45 minutes on the remaining compound machining processes, and then we would like to have a discussion session, right? I would say case study. Okay, we'll go back to the chart that we showed first, and we'll see what are the processes we covered, what are the physical principles there. So kind of recap, summarizing what we have learned so far. I will probably make a group of 2 or 3, then you can try to come up, first you identify what we covered and what are the physical principles of those, and then maybe you come up with 2, 3 idea of maybe 2 idea of compound machining processes and 2 idea of hybrid machining processes. Okay, and what would be the target applications, where you want to use those, and then kind of share with me. I think that would be like some thinking, right? So whatever you have learned and you are applying that. And in the tomorrow I'm going to cover nano manufacturing processes, okay? Mostly nano EDM and some other nano manufacturing processes. So that's the plan for the remaining of the courses. Okay, so let's start. So the contents that we will be covering, so those are some of the, I would say, currently available hybrid machining processes or hybrid micro machining processes, available in the literature. But definitely, there could be some other recent research in other, processes I probably missed, but those are some of the most, widely researched processes. So first, combined micro grinding and micro electrochemical machining. So again, when we say combined, for each processes, 2 physical principles, at least 2, or I would say 2 energy sources are interacting simultaneously. Okay, not one after another, simultaneously. Then you have micro EDM and micro UCM, ultrasonic machining combined process. Then you have micro electrochemical discharge machining. Yesterday, you saw that, and like I forgot your name. Nitesh, yeah, Nitesh demonstrated that. So we are going to learn a little bit more into what's happening there. Then combined laser micro drilling with jet electrochemical machining, which is jet ECM combined with laser micro drilling. Then abrasive electro discharge grinding. So we already know some of those processes separately, so that will help us to understand exactly what is happening. Then abrasive wire EDM, very similar to abrasive EDG, which is for die sinking, and then you have abrasive wire EDG. And there is another abrasive wire ECM process that I included. I've been listed that I just included few slides just after abrasive wire EDM. So abrasive wire ECM is another process. Then you have EDM or micro EDM and ECM combined process. So this is not ECDM process, the process that Prof. Rahman was talking yesterday. So that's a not fully ECDM process, but you cannot also say this is ECM or EDM process. So it is simultaneous, so some sparking, some dissolution, and it is happening simultaneously, but it is not ECDM process. Okay, so I would say simultaneous or combined micro EDM and ECM process. So that's what we are going to cover. So reference materials, again, I used some of those reference material, my papers, or mostly book chapters with Prof. Rahman, and then some of my colleagues, Dr. Sundaram and Kapil Gupta. So I have all those papers also, and I have the lecture materials. So if you are interested, I can put all those in a folder and then share it with you. Okay, yeah, sure, I'll do that tomorrow. Okay, so let's start. So first, laser micro drilling with jet electrochemical machining. Okay, so why we need to do that? Why we need to combine laser micro drilling with jet electrochemical machining? So what laser does? So now we all know, right? So definitely laser is a faster process than the EDM process to make any micro hole or drill. So we saw a compound process where you used laser, to make a pilot hole, right? And then you use EDM to extend that hole and remove all the recast layers and heat affected zone. So now you know that the recast layer and heat affected zone remains a challenge, right? Now in the compound process you used one after another, right? So it is a little bit time consuming. What if I can try to do two physical principles at the same time? So that's the goal of laser electrochemical machining. So electrochemical machining removes material by electrochemical dissolution, right? Because of the chemical reactions. So what happened here is same principle. You use laser micro drilling to make hole, which is a pilot hole. Then at the same time, not after, at the same time, just immediately with the laser micro drilling, you can use a chemical jet, right? If you just put electrochemical solution, then it will be a slow process, right? So you want to increase the speed. So you use a electrochemical jet, okay, just along with the laser beam. So laser beam is making some pilot hole, and electrochemical jet is removing all the recast layers and heat affected zone at the side wall, okay, and then the process just move forward, right? So that's the goal of this hybrid process. So this is two processes that are happening at the same time. So you are using thermal energy in the laser to melt the material and do the pilot hole, and then you are using electrochemical jet to kind of remove the heat affected zone and recast layer, okay, at the same time. So let's look at the schematic. So you know that the laser beam, it focuses on the surface. So the first thing you need to do is you need to focus the laser just slightly before you start passing the electrochemical jet. Why? Because once you pass the electrochemical jet, then it will be a little bit difficult to focus the laser. And even if you focus the laser first and then you kind of start the electrochemical jet, the effectiveness decreases by 20%. The effectiveness of the laser in air, if you consider that 100%, then the effectiveness of laser at that within the electrochemical jet is about 80%. So that means effectiveness decreases. So that's another scope of improvement. Okay, so you are using the focused laser beam, and because it actually the spot size can be really small, so you can actually make the pilot hole small, right? And then electrochemical jet is also doing some electrochemical dissolution and continuously removing the material around the pilot hole, right? That means those are mostly heat affected zone and recast layer are moving continuously. So the whole diameter that you will get is more relevant to the electrochemical jet diameter, right? The laser is making the pilot hole mostly. So the electrochemical jet diameter will control the diameter of the final hole, right? So here, now let's look at what happened, process mechanism. I already explained that, so, but everything is written here so that you can also kind of study. So as I mentioned, the first thing is you focus the laser beam on the surface, right? And those should be coaxial, right? So coaxial, right? That means the center axis for both laser and the electrochemical jet is the same. Yeah. So that's what you are doing. So you first focus the laser and then you start the nozzle, and the laser beam needs to transmit in the jet electrolyte. So that means the electrolyte that you select has to be a medium where the laser can really transmit. The lesser it will happen, like the slower will the process become, right? As we already mentioned that even with the jet electrolyte the authors used, it reduced by about 20%. So usually you use a neutral salt solution, I think sodium nitrate or something like that, which is attainable to laser energy by absorption and scattering, right? So there will be lots of scattering also. Then the jet electrolyte, you align those coaxially, then the mainly the laser is making the drilling process, the pilot drilling process, and then electrochemical jet is actually performing the auxiliary function by removing the recast layer and spatters. So you have to be a little bit careful on how much material you are keeping for electrochemical jet, right? If you are keeping too much material for electrochemical jet, the process will become slower, right? So you need to carefully consider that, okay? So I would say probably the best solution would be you do the laser drilling first, identify how much is the recast layer thickness, and then you identify the jet, how much will be the jet diameter, so that the recast layer thickness are removed. You don't really need to remove too much parent material, using that electrochemical jet, right? So that's how you are going to define. And you know that in laser there could be some defects, but when you are using electrochemical jet together, most of the defects are actually alleviated, and the jet itself can actually coolen the part, because laser is removing materials by thermal energy, so it will become hot, right? So the jet can actually cool the workpiece as well and reduce the defect. So here a little bit more into what's happening. So here you see you have the laser, and then you have the electrolyte jet. Electrolyte jet, and then definitely there are some pressure from the electrolyte jet that also have some action there. And then another variety you can do. So those are the case study we'll talk about. There are some research that actually use some abrasive also, but here electrochemical jet there is no abrasive in this study, but you can probably add another mechanism, right, by adding some abrasive particles within the electrochemical jet, right? Then you have 3 different mechanisms playing role in one process, right? Okay, so then this is in the pulse width, then in the interpulse, the recast layers are removing, and the profile is you are obtaining the profile. So definitely there will be some curve width because of electrochemical jet and dissolution. So we just talked about that. So in order to maintain accuracy, you really need to know exactly what is happening, how much for which which pulse energy you are selecting, and for that specific pulse energy, how much is the recast layer formation, right? And then you kind of come up with the electrochemical jet nozzle diameter. So okay, Now let's look at process capability. Okay, so you see laser, we know that laser actually leaves lots of heat affected zone, right? First of all, here it shows that if you are using just the laser drilling, you see the material removal rate is higher. When you are using the hybrid process, that means you are doing the combined electrochemical jet and also the laser, the material removal rate is reducing. Why? Because the effectiveness of the laser is getting reduced, right? And if you look at the surface and the profile accuracy of the micro holes, machine micro holes. So this is the entrance side, this is the exit side, just with the laser in the air, okay? And you see both entrance side and exit side has significant heat affected zone, and also the profile accuracy is not very sharp. So you see the profile is very blurred, and you can see the taper, right? You can see really the taper. On the other hand, when you are using the hybrid process, that means combined action of laser drilling and also electrochemical dissolution, so you get very sharp corner, but in the entrance side we can still see some heat affected zone. On the exit side we really don't see that heat affected zone. But again, you need to do some study of the microstructural changes in that heat affected zone to see exactly whether that will interfere with the application that you are doing. If not, you can leave that. But I think I really like this picture. This picture really tells the effectiveness of the process, right? So here you see the recast layer, and then you see slightly red heat affected zone, and you can actually remove all the recast layer and that heat affected zone by the hybrid process, right? And it has a very clear edge, right? So that clear edge definitely proves the effectiveness of the hybrid process, okay? So challenges. So what are the challenges? I really think that process works very well for the removal of heat affected zone and recast layer generated by the laser drilling process. Now you need to see how much speed is going down, right? And that is something that you need to think. I said 80%, but in fact it is actually 70%. So that means the material removal rate or the speed, it decreases, about 30% because the efficiency of the laser actually reduced by 30%. But it can reduce the defects caused by the laser drilling. However, entrance side still has some signs of the heat affected zone. The thing that we mentioned, if you use some abrasive, slurry, it will not remove too much material, but it may remove some of those from the entrance side, some of the heat affected zone from the entrance side, okay? Because I think those heat affected zone is not visible on the exit side, so that means the depth of those heat affected zone is not much, right? So maybe you can do little bit of surface finishing on the top, and those heat affected zone are okay, those heat affected zone will be gone. So definitely you can actually combine another action, abrasive action with that to improve the process. But still, I think there are a lot of research need to be conducted in this process, and I think really this process has some, I would say, good scope. Okay, and some of those, I think I was talking to you about mining right yesterday. And I think some of those I talked about, right? Instead of the slurry, just for the drilling, whether you can use the slurry jet, right? We just talked about that in the last class. So it has been tried in this scale. You just need to do it at larger scale for mining. Okay. So next one is micro EDM and micro ECM combined process. Again, we know very well how the micro EDM works. we know very well how ultrasonic machining works, right? From our compound machining processes. Okay, so in the micro EDM process, we know that the material is removed by electrical discharges or electrical sparks. So the material removal rate is slow, and definitely the productivity is very small. And also the flushing of debris becomes a challenge when you go deeper into the part. On the other hand, the micro ultrasonic machining, it uses cavitation process, okay, to like I would say chip or crack the material from the brittle material and then remove the material in that way, okay. And also it works on the because of the ultrasonic vibration, it works on the pressure differences, okay. That means the vacuum created during the pressure differences helps to take out the debris. So remember, you use ultrasonic vibration in the micro EDM process. Here is with ultrasonic vibration, you are just adding some abrasives, right? So instead of just the dielectric, you are using some dielectric with the slurry particles suspended into it, right? Okay. Now remember, in the traditional ultrasonic machining, you really don't necessarily use dielectric, okay? Yeah, you don't use dielectric, you use some other fluid that actually mostly purely water, so that water actually creates lots of vapors, and that helps in the cavitation. Yeah, so your target is to select a fluid, okay, that will facilitate the cavitation, right? But here you are using a fluid that will also allow the EDM process. If you use water, there will be too much electrochemical dissolution, sparking will not be the dominating process. So that's the difference between the ultrasonic machining and here when you combine micro EDM with the ultrasonic machining, right? You are not using water, rather you are using dielectric. So cavitation will still be there, but less significant than the ultrasonic machining, and there will be some abrasive action also this time, right? So I would say like three different physical principles of material removal. One is electrical discharges, one is cavitation, and then there is abrasive actions. So all three actions actually are taking place, but two are primary, and one is secondary. Abrasive action is mostly secondary, but the other two actions are primary action, primary mechanism of material removal, right? So that's kind of the micro EDM and micro ACM, and the goal is to obtain higher aspect ratio micro holes than the micro EDM process itself or micro UCM process itself can do. Remember, 1 + 1 = 3. If it is 1 + 1 = 2, then it's not a hybrid process, right? Maybe in sequential process, sometimes it can be 1 + 1 = 2, but hybrid process, it should be 1 + 1 = 3, more than what the two individual process can do, okay? So definitely it will remove the recast layer and heat affected zone. It will make the process faster, okay? So those are the things needs to be done here. So just let's look at the process mechanism. So here one important thing is another thing is slightly different. In most of the cases in ultrasonic machining, the vibration is applied to the tool, okay? But when you are using ultrasonic vibration assisted EDM or micro EDM, you mostly apply it to the workpiece, because in micro EDM we use comparatively smaller size micro electrodes, and that can really affect the accuracy and the sparking process. Okay, so here you see you have that transducer, or it is more popularly known as horn. In industry, if you say transducer, maybe some like workshop operator may not understand, but if you say horn, so they will understand, yeah, right? So yeah, so this is horn, and then at the tip of the horn you are using the tool or electrode this case, for the combined process. Then you are using dielectric fluid. Remember, you are not using water that is used mostly in ultrasonic water-based slurry, but you are using some abrasive particles mixed with the dielectric, fluid here, so that the both EDM and the ultrasonic machining is happening at the same time, and that needs to be connected to the EDM pulse generator, the tool and the workpiece. Otherwise, it will not spark, right? So this is kind of the basic, setup. So you are just modifying the ultrasonic machining setup, adding that, with a pulse generator to kind of concurrently supply some discharges. So if we look at the gap phenomena just here, so in the gap phenomena, what you have the spark, you have the abrasive particles, and the abrasive particle will have some abrasive actions there, and then there will be some cavitation also here, and then there will be some sparking in between the tool. Okay, so all three actions actually will cause the removal of the material. Okay, and some of the abrasive particles you can use boron carbide, silicon carbide, or aluminum oxide. But again, you can use deionized water. But if you use water, I'm sure the EDM portion will slow down. The dissolution portion will actually be more dominating here. Okay, so this is kind of the physical principle. So as I mentioned, the material removal is a combined action of electrical discharging and cavitation process, and mechanical polishing by abrasive slurry is also a third process, secondary mechanism taking place here. So this is real hybrid process. So you see several physical principles or energy sources are working simultaneously. Okay, so this is kind of the real hybrid process. Yeah. Because of the vibration.
I joined with the pressing process. So what is the means how we can go with the long time press?
So yeah, so that is the reason why we don't use ultrasonic vibration on the tool during the micro EDM, right? But maybe you need to do a little bit of a study in some of the papers of just the ultrasonic machining. Okay, just ultrasonic machining, how they put the tool electrode, because for them it is not breaking. But one thing I think I saw, you can have the larger base than a smaller electrode. So that has the support, because I work with ultrasonic machining, and they have a tool which is very heavy. So they have about 100 or more than 100 actually, about 200 arrays of electrode, and then they leave a lot of support around. So it is, I would say, about probably 4 or 5 inch by 5 inch tool, and then when they made the array of electrode, it is within maybe 3 inch by 3 inch. So they kept a lot of space at the side. So that's why I said probably they also face the same challenge. So you probably need a stronger base that in the tool holder. Yeah, so you can try that. Yeah, yeah.
How about the flushing mechanism here, sir? Because we are using abrasive particles.
Yeah, so the pressure created, so that's how the cavitation happens also, right? The main like mechanism of cavitation formation is there will be some heat generation, and then there will be some pressure differences, at the gap and at the outside, right? So that will create some negative pressure, and that will create some bubbles, and those bubbles will collapse. So the negative pressure creation will actually help, flushing out of debris. So you can use some, side flushing, but because it is ultrasonic vibration, right? So it will be able to remove the debris. Yeah.
Because during machining process, some debris will also be
Yeah.
and abrasives will also be flowed into that machining process.
Yeah, yeah.
So it can deorient that surface of hole.
You can.
It will lead to the deorientation of that surface also.
So so usually, you are recirculating all the time, right? So, so when you are recirculating, you are separating the debris and you are keeping the abrasives, right? So, okay, abrasive is non-conductive most of the cases, okay? And based on which material you are machining, the debris can be conductive or non-conductive. But again, particle size is also another thing. If your debris particle is much smaller than abrasive particle, you can easily filter those out and recirculate those abrasive particles. So there are ways you can actually control that. Okay. Okay, so let's continue with the process mechanism. You just mentioned how the flushing is happening. So here it says the high frequency pumping action of the vibratic surface actually, it can create some pressure differences, and that actually accelerates the slurry circulation. Exactly what we just discussed, right? And which actually also helps in reducing the machining time and also making the process faster. The pressure variation in the gap lead to more efficient discharges, okay, because of the pressure differences which remove more material. The heat affected zone is reduced because of the abrasive actions and also the cavitation actions. Then you will have less thermal residual stress, less micro cracks, and fatigue resistance improved, okay? All those because of the abrasive action of the slurries. The abrasive action is just like sandblasting, right? You are removing, the recast layer and residual is, you are inducing some good compressive residual stress, but you are taking out the tensile residual stress from the surface. So all the good, things you are considering in the hybrid process. So that's how you define the hybrid process. So here, just an example. So we all know how the EDM, it is possible, as I mentioned, micro EDM has improved significantly. In industry, it is now standard. Okay, so now micro EDM really can do a lot of things that other processes we are saying. You may not need any compound or hybrid process. Maybe hybrid process sometimes you need, but most of the cases micro EDM has improved a lot. Okay, most of the industry, like you have micro EDM machines from many large companies, right? Makino, then Mitsubishi, Panasonic, then Sarix, then the Chinese company also good. Sorry, no, I forgot. Yeah, so all of them make very good micro EDM machine, right? And they can produce industrial grade parts. Okay, so micro EDM has improved a lot. Okay, so now you see this is from 2000. Now it is 2020. Right, 2022-3 now. So micro EDM process has improved significantly. But here, when they did, you see that I'm sure micro EDM process can now create the surface finish like that, even better. But when they did that, so the micro EDM drilling, it can create the inner surface hole, which is rougher. On the other hand, when you are using, the combined or hybrid process, you can actually get a smoother surface finish. But see some challenges. You see one of the wall, the wall is not very sharp because of the chipping action, right? Because both abrasive action, when you are using abrasive action, there is some problem also, all the edges or also some of the, I would say, anywhere there is elevated, it will try to kind of make it level, right? So that's the I would say behavior of the abrasive jet machining. So you may end up, getting some chipping of the sharp corners, okay, or sharp edges. But other than that, it can actually give you very good surface finish in the cavity and also helps you to get a much higher aspect ratio. So that's kind of the goal of this process. So I already mentioned the process capabilities, machining high aspect ratio micro holes in difficult to machine materials. But if you want to, dominate the EDM process, it has to be electrically conductive workpieces, right? So I think I mentioned it can, the good thing is it can really machine lot of holes at the same time. Micro EDM, it's difficult, okay? Because in micro EDM, the flushing becomes a large issue, major issue when you are machining arrays of holes, okay? But this ultrasonic machining is used actually for making arrays of holes. So when you combine those two processes, it can be really good, you know, for making arrays of holes. The overall material removal rate can still be slow, so future research should, you know, focus on improvement. Then profile and corner accuracy are subjected to more wear. We talked about that. So if you can come up with, you know, some like innovative technique how to improve that, I think that would be something important contribution also. Okay. So challenges, I think I already gave you some directions. There is a lot of improvement that can be done, you know, through optimization. Maybe, you know, the recent optimization techniques. There is a limitation in the slurry fluid, you know, as I mentioned, which can also work as a dielectric fluid for EDM. The effect of abrasive particle slide, the slurry fluid, all those can have actually impact. So far it is, you know, most of the ultrasonic machining is actually for like holes, okay? But if you want to do some like little bit different cross-sectional profile, okay? Then the profile accuracy, corner accuracy, that will, you know, come into play, right? And that may be a little bit challenging. So I think there is more research needs to be done in that area also. Instead of just circular hole, why don't we try, like for example, a plus sign or you know, a star sign? Try to machine that and see what happens to those corners and sharp angles, and then that will be something interesting, you know, to study. Okay. Okay, so let's talk about combined microgrinding and microelectrochemical machining. Again, very similar. Both those processes are very similar. So when you today in the case study, I really want to see, you know, some kind of I would say crazy ideas. Okay, so sometimes crazy ideas can be really, you know, good ideas, or I would say breakthrough ideas. Okay, rather than little bit of incremental improvement, whether you can really, you know, come up with some breakthrough idea. Okay, and then try. Okay, so combined microgrinding and microelectrochemical machining, I think very similar to the first one. Which one? Yeah, but all the processes looks very similar, right? When you learn about so many processes. So as you can see from the name, you are combining microgrinding and ECM process together, but remember, those are not one after another. You want to do it simultaneously. So how can you do that? You know the microgrinding process. We have the microgrinding wheel at the end of the micro tool, right? So you can use that to machine deeper holes or any slots. So that's the microgrinding process. And usually in microgrinding process, there is no requirement for you know, fluid material. You can just use any fluid material as a coolant. Now, what about if you select a fluid material that is like electrolyte? Okay, that is electrolyte, and you are actually, you know, doing the microgrinding, like you are passing some electricity. So you are connecting the tool and the, you know, workpiece. If it is electrically conductive, you are connecting that as a two polarity. If you want to do non-conductive, just like ECDM, you add another, you know, auxiliary electrode, you know. So you can modify the microgrinding process by adding a electrolyte, okay, and then connecting that with the pulse generator, and then that process will become the combined microgrinding and micro ECM process. So the goal is, microgrinding is a slow process, right? And micro ECM is another slow process. But when you are adding both, you are actually kind of trying to improve the material removal rate. Both process will give you good surface finish, so no problem with the surface finish, but you are just, you know, trying to increase the material removal rate for two slow processes by combining them together. Okay. So process mechanism. So usually I would like to see the picture side by side here. So this is the picture, but I think we'll talk about the process mechanism, material removal mechanism. So as you can see, a spherical metal tool with coated diamond abrasive particles will use as a cathode, okay, and which rotates at very high speed and removes material, electrochemically and mechanically on a predefined pilot hole. So in order to make this process faster, you can use a predefined pilot hole first, okay, and then you can do that. So the pilot hole, if it is electrically conductive, can be done by micromilling. If the pilot hole is electrically non-conductive, then you can use micro ECDM or some other process, to machine the pilot hole. And then you are using that spherical metal tool with the abrasives are, diamond abrasives are connected to that. So that means this is very similar to the grinding tool we discussed. Okay, so it has the diamond particles. It is connected to the metal matrix, right? There is a binder, mostly nickel binder, that hold all those diamond particles. Okay, and then nickel binder itself is conductive, but the diamond particle is electric non-conductive. So diamond particles is non-conductive, and that's how you assure that it is not electrical discharge, it is some mechanical contact in between the diamond particles and the layer. And electrical discharge will be from the nickel binder, right? So you have metal that will cause electrical discharges, and then you have some protruding diamond particles which are not electrically conductive, and they will contact, right? They will contact the sidewall. So there is some mechanical actions also. So you have mechanical grinding actions and electrochemical dissolution, right? So there. Okay. So this is important. So this is kind of, again, taking the idea of electrochemical discharge machining that I think we'll be covering after this. So the tool will work as a cathode, and the workpiece perform as an anode. And the abrasive diamond particles are not electrically conductive. That's what I mentioned, and then it will have some mechanical actions. And this establishes a small gap between the two nickel layer and whole sidewall, because those are protruding out. So here, this is interesting. So the material removal mechanism happens mostly on the two phases. So if you look here in the picture, the bottom one, the first phase, when the machining has not happened yet, right? And the second phase, there is some machining already there, and then third phase, there is no machining is happening there. So what exactly happens? So when you start the process, the electrolytic action actually starts, okay, because there is already pilot drilled hole, right? Then there is, the electrochemical or electrolyte is passing through. So the electrolyting action begins when the gap is filled with the electrolyte. As soon as the gap is filled with the electrolyte, it is connected, the tool to the cathode, workpiece to the anode, and the electrolytic action actually starts, and electrochemical dissolution starts. And yesterday during ECDM process, you saw what happens, in the electrochemical dissolution, right? So there are some, bubble formation. So in this case, the passivation film occurs on the microhole surface due to that passive, sodium nitrate as an electrolyte. Okay, so some passivation films due to the bubbles will happen on the microiridium surface. And in the phase 2, so remember, in the phase 1, there is no abrasive action is still taking place, right? And then phase 2, it is combination of electrochemical actions and the abrasive actions, right? So the abrasives are actually removing that passivation film, okay? And also there is some electrochemical dissolution that are happening together. and the, let's see. So as the abrasive tool goes downward, the gap decreases until abrasive on the tool base comes into contact with the workpiece. Okay. Then abrasive grades remove the soft and non-reactive passivation layers. Okay. So that's what we mentioned, and then it exposes some fresh material, so that then there is more passivation film on the fresh material, and it removes, so that it continues. Now, why it continues? One thing you need to be, one thing you need to make sure that above the grinding wheel you have some conductive metals, right? Although you reduce the diameter so that to increase the gap, but this is not electrical discharge. This is electrochemical dissolution. So it will still take place. So how you can avoid that? So you just make sure that none of the conductive layer is coming, after machining is happening. All the tool shank, you just use some kind of coating. Okay, you just use some kind of coating on those to avoid the electrochemical dissolution. If not, the tertiary, I would say, the third physical principle, will try to kind of work there, and it will affect the profile accuracy. From the very beginning, we are talking about that micro ACM gives very good surface finish, but the rate of dissolution, is difficult to control, right? So you have to be careful on that. So in the first phase is just before the abrasive actions takes place. In the second phase, combination of electrochemical dissolution. So first phase electrochemical dissolution only. Second phase electrochemical dissolution and abrasive actions simultaneously. And in the third phase, if you don't do anything, again electrochemical dissolution will take place. It will be smaller because the gap is wider, but it still will take place. So you need to put some kind of protective coating there to avoid any kind of electrochemical dissolution. So that's kind of the material removal mechanism. So it says if the tool is not insulated, the electrochemical dissolution will continue on the top portion, in the phase 3, because electric field is already there, okay, and it will create some kind of taper hole. So you don't want to do that. Okay, so this is kind of the process mechanism we discussed in detail. So now let's look at the hole. Okay, so this is kind of the entrance side, and you don't see some kind of heat affected zone that you saw in the first process when you use ECM with laser, right? But here you don't really see that. So the entrance and also edges are very good. Here also you see the edges are also very good, right? So because you put some kind of coating to avoid any kind of electrochemical dissolution after the abrasive action. It could be before the abrasive action, then abrasive action will make it very clean, but after abrasive action you control the electrochemical dissolution, then it should give you very good surface finish, right? So that's the kind of the process capabilities. Here definitely the advantage is profile accuracy, and corner accuracy that we are talking about. For other processes is a challenge, but here that challenge is overcome, so you will be able to get micro features with sharp edges without any bars, right? So corner and profile accuracy can also be higher. So far it was tried for small holes in difficult to cut materials, but definitely you see the aspect ratio is not very high here, so you can also work on improving the aspect ratio, but also in order to just claim that it has good profile and corner accuracy, I think it would be better to create some kind of complex profiles. And then remember, in research, this is one suggestion. Always remember, in research, try to demonstrate what you are claiming. Try to demonstrate that quantitatively, not qualitatively. So I showed most of the picture qualitatively, but this is I learned later, right? This is one of the suggestions I learned over the time, and now I make sure that I kind of try to follow that. many things can be done qualitatively by showing pictures, but if you think how you can actually present that quantitatively, maybe surface roughness, maybe for corner profile you saw this is good profile, but what about you maintain the circularity, you just measure circularity, right? So if it is very smooth, circularity is in the profile of a hole, the gap, the difference between the bottom and the top, right? So you can say that the circularity is so good, 1 micron. Or so try to come up with a quantitative value, okay, always. So this makes your research very good. If you present qualitative, you are just claiming without any proof, right? But when you are putting any quantitative measurements on anything, okay, that becomes really stronger claim, okay, and very difficult to deny that claim. So just remember that, okay. So as I mentioned, all those things we showed, as a qualitatively, but it can be, done like corner and profile accuracy. Then you claim the sharp, it can be able to make sharp edges rather than just showing that, okay. And also I think there is some overcut, here. So that's something dimensional accuracy should be, considered. So I think I already talked about the selection of electrolyte, abrasive particles, bonding materials. All those are important factors to be considered for future research. Coating should be provided to the shank of the tool to avoid electrochemical dissolution. We talked about that. Then there is a risk of loosening abrasives due to mechanical action, right? So because electrochemical dissolution may also remove some material from the binder material, right, over the time, and that will loosen the abrasive particles, and that can also cause some kind of problem.
So can you go with the ductile material?
Yeah, most of the cases, yeah, ductile material you can do, because that is not doing any mechanical action, right? So ductile material should be fine. Okay, now we come to the microelectrochemical machining that you saw in the lab in the last class, and some of the concepts that we already discussed there. So the microelectrochemical discharge machining process, it involves a complex combination of electrochemical reaction and electrodischarge action. Now in the last class, I think one of the students were asking, it is not conductive, then why or how electrical discharge is happening, right? So we'll kind of talk about that, right? So when the coating film, covers the tool surface, right? It actually doesn't allow the electrochemical dissolution that time. So, but you are passing the electricity through that. So it will starts to kind of, spark from the tool to the film, and it will break down the film, and then again bringing the tool, fresh tool into contact. So here, so the combined process provides definitely lower electrode wear, higher material removal rate compared to single micro-EDM process. And although micro-EDM and micro-SCM only machine electrically conductive materials, this can be applied for both conductive, electrically conductive and non-conductive materials, right? So that's kind of the beauty. So yesterday you already showed them, right? You machined some titanium, alloys, and at the same time you showed machining glass, right? So this is kind of an extension of the capability. Definitely 1 + 1 = 3, right? So it's an extension of the capability. So it can be used to machine non-conductive ceramic and glass, which make the process more familiar. So if you are machining just titanium alloy, maybe you will just machine using EDM, right? But if you are machine non-conductive ceramic, you need to go micro-ECDM. So micro-ECDM process, it may have it has higher material removal rate from micro-ECM, but better surface finish from micro-EDM. So it took two things, that are better in two processes, and then also it actually extends the process for non-conductive materials. So it's really 1 + 1 = 3 scenario. There are some challenges in the micro-ECDM process that I have seen, but I will talk about that. So process mechanism, see, is step by step. So the electrochemical action helps in the generation of positively charged ionic gas bubbles like hydrogen. Then electrical discharge action takes place between the tool and the workpiece due to the breakdown of the insulating layer of the gas bubbles. So this is mostly when you are machining electrically conductive materials. Then we'll talk about electrically non-conductive materials. So the DC power supply voltage is applied between the tool and the anode. Then in the ECDM process, anode is made up of inert material, where cathode is normally made up of copper, and you can use either acidic or alkaline or neutral solution for ECDM. Now let's look at here. So exactly what he showed in the last in the yesterday. So you have the tool electrode, negative. You have the workpiece. Then you have another counter electrode. You saw he put a counter electrode to the side, and then you have the electrolyte. This actually shows you, the basic. This shows you the waveform. When you apply the voltage, it goes there, and then it drops, and then it continues. So it actually tells you both electrical discharge and electrochemical dissolution is happening here. Now here you see the gas bubbles actually forms around the tool, and then there is some sparking actually that tries to form at the interface of the workpiece and the gas bubbles, right? So now here, so what happened when you apply the voltage, okay, the hydrogen gas bubbles actually take place, and it goes to the cathode tip, and then when the voltage you apply goes beyond its threshold voltage, the hydrogen gas bubbles actually increases significantly at the tip of the cathode, and then the nucleation site in the density increases, current path gets restricted. So when the current path gets restricted, okay, because of that hydrogen bubble, that time the electrical discharges takes place, and it tries to remove that thin layer. Okay, so that's what it says. So this line actually is very important when you are machining non-conductive material, right? So it says the nucleation site density increases, current path gets restricted between cathode and electrolyte interface, causing the discharge to occur at that interface. So that's the mechanism that helps to remove material in the electrically non-conductive material. Okay, so that's the phase that is important. Thus, the discharge in ECDM always occurs when the voltage in the electrolyte cell is increased beyond the threshold value. Okay, so there should be a threshold value of the voltage. Okay, and above that voltage, it will kind of create a resistive layer to the current, and that time it will starts to spark, and until it removes that layer, and then the process actually starts again. Okay, so that's the continuous process it's happening, but those two are the main reason that ECDM process can be used for electrically non-conductive materials. So ECDM process, some of those are really controlled, some of those are not so much controlled. So here the ECDM process of complex features on the glass. So you can see that you can make some pyramid or some micro cavities. Okay, so again for research, again this is another suggestion. Most of the cases, for research we try to kind of run very simple experiments, right? Because our goal is to show the proof of concepts. But in industry, one of the reasons they don't value our research is because we don't really create the real life part. and show, right? So they always talk about that. Now, and yesterday I was talking to your advisor, about that as well. Professor Das, right, is your advisor, yeah. And yeah, he was saying the same, in industry, sometimes they don't want to, value what we are doing, but we are showing them the path, right? We are showing them the path. But one way you can actually avoid that, okay, in your publication, and also it enhances the chance of the publication to get accepted in a good journal. So you do all the experiments, all the science using simple experiments that you want to do, but plan for one demonstration where you can show the capability. You don't need to do any research when you are doing that. You are just spending, probably 1 day or 1 week, to make that, and you just mention that, whatever we learn from our research, from the science, we use those understanding to make this. So this demonstrates the capability of the process, and then everyone will accept that. Okay, you just machine a small like hole to do all your experiments and everything, but at the end you kind of demonstrated what the process can do. So that's a good way to present any paper, or like attract the reviewer for a paper. For any paper, you just do some slot making, hole making, simple experiments to study the science, and then at the end demonstrate a complex features that this can make. Okay, you may need to do a little bit of extra effort, but that will help the paper to get published in a good journal. Okay, so this is kind of, so something like that. Okay, like the top two pictures. So this is again, I think Professor Sundaram, Murali Sundaram. So this process, electrochemical discharge machining process, now it becomes itself as an independent process, and now you are trying to use other sources to make the process even more hybrid, right? So there are we talked about a magnetic assisted, or some kind of vibration that you can apply. People have already done that. So here, so this is vibration assisted electrochemical discharge machining, where actually they found that they are able to increase the aspect ratio significantly after using the vibration assisted ECDM process. So on the glass material. So this is kind of ECDM, but again you can see the taper. The entrance is 180 micron, the exit is 40 micron. So it's a significantly taper. So how you improve that? This becomes tapered because the electrochemical dissolution is not controlled, right? We talked about that. If you don't do electrochemical dissolution like in a controlled way, then when you are machining here, some electrochemical dissolution is still taking place on the areas that you have already machined, right? So that will cause the part like machined hole to be tapered. So how you can get rid of that? We talked about adding some kind of coating there, so to protect that. So this is something can be tried. And for this one, again, this is powder mixed ECDM process. So again, another hybrid process. ECDM process itself is a hybrid process, but you can use two assistants, right? One is vibration, one is powder mixed, we showed, right? But for magnetic, in order to use magnetic, the material needs to be magnetic. So that's has another limitation. But here you can see that the surface finish actually improved, after you use the abrasive particles. Usually, the surface finish is not very good in the ECDM process, because although it is combining the principle of EDM and ECM, but ECDM process is a unique process. Okay, it's a unique process of material removal, right? Because what it creates is some electrochemical reaction to create a film, and then discharge machining to break the film, and then proceed. So when you do that, breaking the film, definitely the surface finish is not very good. Okay, so you most of the cases ECDM doesn't provide very good surface finish. So you can use some powder mixed ECDM process, to improve this process further. Okay. So process capabilities, as I mentioned, we showed that it can create some complex features with high accuracy. It can also, create some high aspect ratio where the accuracy was not very high. So there are some, challenges, but the accuracy of ECDM process, it can be lower than micro EDM process, because micro EDM process is very precisely controlled process. Okay, so ECDM process has not, I would say, now some industries are trying to do ECDM in the industrial scale, and I think that time it will become, very developed in terms of, accuracy. But most of the research was not able to demonstrate very high accuracy for micro ECDM process. An expanded version, we already talked about the powder mixed EDM and vibration, powder mixed ECDM and vibration assisted ECDM. They can further improve, the performance of the ECDM process. So challenges, we talked about several challenges, right? Uncontrolled sparking process on the hydrogen film and bubbles make the dimensional accuracy a problem, right? And also the surface finish. So how you can control that? Then electrochemical dissolution, on the area that has been already machined cause some, issue with the dimensional accuracy, make holes taper. How to control that, right? It is used for wide range of materials, which is good, but the performance can also vary from materials to materials. You already saw that, right? Yeah, so when you are machining electrically conductive materials, when you are using glass, the performance is significantly different, right? So how you can actually improve that, for different materials. So selection of tool material, electrolyte is important, controlling the bubble formation. So usually now you are, by voltage, you are controlling the, bubble formation, right? But it can have direct control on the material removal mechanism also. So you need to have very good understanding of, the bubble formation mechanism and the factors that are influencing the bubble formation mechanism, right? Okay, so what is the time? 10:30. Okay, so we have a few minutes. So I'll cover, I think, 2 or 3 more processes, then we'll take a break. Okay, yeah. Okay, now abrasive electrodischarge grinding and abrasive wire electrodischarge grinding. So what it happens, we already know the very similar process as abrasive ECM. We already know that we can use the abrasive, grinding wheel, okay, where you have the tool shank of electrically conductive materials, maybe tungsten carbide. Then you have, in the wheel, you have the nickel binder with, diamond particles as abrasives. And then we use some kind of, electrochemical, like electrolyte for that. We just covered that. So just consider the same, but here we are going to use electrodischarge grinding with the abrasive action, okay? So it combines the EDM and the grinding process. In the EDM process, it is electrical discharging that actually removes the material or electroerosion. And on the other hand, for the grinding process, it is the mechanical action of the abrasive particles that cause the grinding. So when you combine those, you are actually making the process abrasive electrodischarge grinding process, okay? So usually EDM creates a rougher surface that needs some kind of grinding operation, and from there actually the process comes from. So you do the EDM and grinding simultaneously so that the recast layer is removed and heat affected zone is removed, and it actually gives better surface finish, okay? And also in terms of material removal rate also, but I don't know, I cannot say that it will increase, because when you have some abrasive particles, the spark gap between the conductive metal and the wall actually is increasing, right? So, but we can expect that the material removal rate can be also improved, but definitely the surface finish will improve, and also how to say, like the heat affected zone will be eliminated. Now here it shows a simple schematic. So if you have a tool like grinding wheel, you have the grinding wheel where like non-conductive abrasive particles are like how to say, non-conductive abrasive particles are on that metal matrix composite, right? So that's kind of the abrasive mechanism. Then for EDG, again, you just connect those with the pulse generator, right? And then you supply the electrical sparks, and then it will remove the material. And when you combine those two, you actually are getting abrasive electrical discharge grinding. So very simple, I would say, very simple to understand, but there are a lot of study needs to be done if you really want to see what's happening at the interactions. For remember, if you consider modeling, the modeling of hybrid processes are very challenging, right? Because it is simultaneous actions. Okay, so there is always a scope, of doing some mathematical modeling for those hybrid processes. Okay, so and as I mentioned, the hybrid processes just before the additive came, the hybrid processes was the cutting edge research. Then suddenly additive came, and it is not saturated. There is still a lot of opportunities, on the hybrid micro and nano scale machining. Maybe when people will start saturating with additive, which is happening, then people will again come back to, some of those hybrid machining processes. But they are already talking about hybrid machining processes, like for hybrid AM and subtractive, right? But okay, so this is simultaneous action, mechanical action, and abrasive particles. I think we talked about that. So now let's go a little bit. This is another picture. The left one we already showed. Now here, I think I already mentioned, so you have metallic wheel, which has the metallic binder, most of the cases nickel binder. Then you have non-conductive abrasive grain, right? And then that's the difference. That's the thing is challenging, as I mentioned, that I cannot really say that here, right? So this is interesting. So this is the gap, right, for abrasive particles, and this is the gap for spark, right, electrical discharge spark. So this is for spark. So it is not, so what I want to say is that it is not controlled in a way that the sparking will happen first and then grinding will take place. If it is controlled that way, then definitely the material removal will increase. But it is, I would say, uncontrolled, right? So that's why electrical discharge may not be as effective, as it was supposed to be. So that's why I am, doubtful whether it will have much higher material removal rate than the EDM process itself, right? But remember, for ECM, we showed that, okay, the electrochemical dissolution happening, and so in that way it will improve. But here, I think there is a scope of improvement. Okay, there is some scope of improvement that in some process only EDM will go, and then there will be some combined process. If you can ensure that, I think then it will be probably, like more effective. Okay, but yeah, so that's how the process works. Okay, now it looks the process capability, but what I said, you can control that. So that means I just made the doubt that, okay, the EDM process may not be dominating, right? Because the spark gap with the metal matrix and the boundary is smaller, but the protrusion, the gap is, sorry, am I wrong? No. So the gap between the protruded abrasive particle and the boundary wall is smaller, but the other gap, is larger. So sparking may not be very effective there. So if you are using smaller voltage, right? You already know if you are working on the EDM, there is a direct correlation between the gap voltage and the spark gap, right? So you already know that. If you increase the voltage, and if it is servo controlled, it will actually open up. It will open up the gap. So for this case, if you are using comparatively smaller voltage, okay, the abrasive action will be the dominating action. Okay, so the abrasive action will be dominating action. You will get comparatively better surface finish, but slower material removal rate. If you really want higher material removal rate, then you need to use higher voltage. Then if you use higher voltage on that larger gap, sparking can actually be more effective. Does that make sense? Because there is a direct correlation between the gap and the voltage. So in order to create effective sparks in the higher gap, you need to apply higher voltage. Exactly what I showed is said here. So if you are using comparatively higher current and I would say higher energy, then you will get higher material removal rate, and the process will mostly dominated by electrical discharges. On the other hand, the surface finish will not be that good. But if you want better surface finish, okay, then you can actually select the parameters, EDM parameters, in a way that the sparking will be secondary, but the abrasive action will be the primary. So that's something also very interesting that you can actually control. So they showed it very well with the arrows. So if you have more grinding to take place, that means grinding is the primary mechanism, then you will end up with good surface finish, but slower material removal rate. On the other hand, if you have more EDM, taking place, then you will end up with comparatively rougher surface but faster processes. So just like regular machining process, maybe you can actually do some roughing first, then finishing, right? You go with higher EDM settings as a roughing, and then you reduce the electrical energy parameters for EDM, and then it will go into the finishing step. Then you will get a good surface finish. So process capabilities, definitely it can machine very hard materials like engineering, ceramics, sintered carbides, and metal composites. Now, in order to do ceramics, sintered carbide, you may need to do little bit of other techniques, like you need to probably do assisted electrode method, right? Where you can actually add a conductive layer that will help, like to maintain the electrical conductivity required, okay? The material, I think I talked about that. The material removal increases significantly in ADG compared to conventional grinding. However, the surface finish can be compromised if you want to increase material removal rate, because the electrical discharge will be the dominating process. Based on the primary goal, you can really select whether you want to shift towards more surface finish, that means more of the abrasive action, or you want to go towards more on the EDM discharges, right? So if the primary is machining speed, then apply higher current and higher discharge energy for EDM to take place, and vice versa. So yeah. Okay, now as I mentioned, the same process can be done for ECM process, right? So I didn't really add separate things for ECM because we covered almost very similar thing in just different arrangement. So everything same, just instead of EDM fluid, you can use ECM fluid, okay? And then it will be a ECM process. So here definitely they try to do some modeling action, but again here you see the grain, the grain will be the dominating mechanism, but this is better than ECM in a way. In ECM, definitely the gap has some effect, but even it is slightly larger gap, there is no issue, right? Electrochemical dissolution can continue. So for EDM, you have to kind of increase the energy to make sure sparking is happening. But for ECM, the electrochemical dissolution will happen. Okay, so electrochemical dissolution will happen, and then the final dimension will be actually determined by the abrasive, how much abrasives are protruding. But I think in terms of dimensional accuracy, this process will be a little bit difficult to control because of the ECM process. But here, the benefit of abrasive assisted ECM over abrasive assisted EDM is that abrasive assisted EDM actually it can have some like harder surface micro hardness. On the other hand, if you do electrochemical dissolution, it actually removes recast layer. Remember, for removing recast layer, electrochemical dissolution is a very effective process, even sometimes effective than some mechanical abrasion. Okay, so it really can remove all the recast layer thickness, all the heat affected zone, and reduce the micro hardness of the workpiece surface. Okay, and which can also reduce the tangential and normal forces for individual grain. So what it tells you that if you consider the cutting force analysis for the grinding portion, when you are using abrasive assisted electrical discharge machining, there is more chance of the grains to come out, okay, or loosening from the matrix, okay, because EDM process creates some recast layer, and those have comparatively higher surface hardness because those melt and immediately solidify, right? So those has slightly higher surface hardness than parent material, and that can actually be a little bit difficult to remove using those abrasive particles, right? And that can actually put lots of cutting forces, higher cutting forces on those abrasive particles. On the other hand, for ECM, the electrochemical dissolution is happening, and recast layer probably very minimal to no recast layer, so the material is comparatively softer there. Okay, so that's the benefit of abrasive assisted ECM process over abrasive assisted EDM process. Okay, so the abrasive assisted EDM process, probably the tool life will be comparatively longer, especially the grinding wheel part. But there are some challenges because electrochemical dissolution is difficult to control. So here, so it just shows you the reduction of surface micro hardness when you are using abrasive ECM process. Challenges. The process has good potential and it can be modified to both abrasive assisted EDM or abrasive assisted EDM by careful selection of the fluid material, whether you are using dielectric fluid or whether you are using electrolyte for ECM. The sparking for the EDM can be difficult. I think I already discussed those because of the insulator abrasive particles are protruding out from the electrically conductive tool, so the gaps are actually different. The applied current can have direct effect on machining performance. So if you can increase the applied current, then you can actually make sure EDM is taking place and you can improve the material removal rate. The interactions of the two processes needs to be understood very well, right? So even some of the things we talked, but when especially if you're doing PhD, it is your job to kind of validate by mathematical modeling what you are talking, right? What you are claiming. Like for example, I remember when I did some modeling in the powder mixed EDM during my PhD, so we saw that, okay, we tell that spark gap increases in powder mixed EDM. How? So I did some modeling in one of my paper, I think in powder mixed EDM paper from 2009, you probably will see. So then we showed that yes, spark gap really increases when you use the powder mixed EDM process, right? So, but there are so many things I could not show that can be done also. Like so whatever you are claiming, if you can just show that with the equation, then that's pure contribution, in your PhD research. Okay. Okay, I think this is the last one for like hybrid machining processes. Then we can take a break. Okay, so abrasive wire EDM, very similar. Instead of tool, now you have, like for example, zinc coated wire. So when you are putting some zinc coated wire, or when you are extruding the wire material, what you are doing is you are adding some abrasive particles there, right? So the wire material. So yesterday in the lab you saw that wire EDM, right? There is a wire material. Just consider that wire material is brass and very smooth. But instead, if of having it is smooth, if you have the abrasive particles on it, okay, just like abrasive particles, when I think you are a kid, you have some goody, right? And sometimes you kind of play with another friend to cut and you put some kind of abrasives, right, on that to make it a very similar concept. So if your wire has some abrasive and then you are doing the wire EDM process, that's what we are talking about, right? So abrasive wire EDM. The goal is definitely the wire EDM, the discharging will take place, but the abrasive action will have some concurrent, but secondary, application, so that you can both improve the material rate slightly, but the main goal is to reduce or eliminate the recast layer that is generating during the wire EDM process.